Hello, everybody. All right, so we're getting into 2D projectiles. So we have velocities that are at an angle going up or down or landing with a combination of velocities in the horizontal direction, moving back and forth, and the vertical direction, moving up and down. When you have both kinds of motion, like projectiles do, you end up with a velocity that's at an angle. So we're going to learn how to calculate some of that stuff. So here's the worksheet that we started today. And as you can see, there's that. This one we started today, and we did number one together in class. So here's number two. You guys are working on that pretty well by yourselves. Most of you guys are totally on top of it, but some of you need a little bit more help. So hopefully this will be helpful. All right, so let me get into it. A slingshot is used to launch a stone horizontally. Um, horizontally from the top of a 20-meter cliff. So the stone lands 36 meters away. Okay, so you got the typical cliff. You've got a slingshot. The drawing of that's not that important, but I want to have some fun with it. And you got a rock there, guy pulling back, and then it gets shot that way. So you get your stone flinging that way, and we know that it lands 36 meters away. Hopefully you're starting to recognize the vocabulary that 36 meters away means the x direction, delta x from there to there, where the projectile lands is 36.0 meters. So we can see that 36.0 meters. All right, and that's all we know, right? So we're supposed to find what the initial velocity was in the x direction, and then what is the speed and angle of the impact. And by that we mean this thing, when it lands, we know it's going to come in at an angle, which really means it's going to be a combination of two things. A combination of the, let's go blue for back and forth, combination of the horizontal velocity, and a combination of the, let's go green for go down, I guess, velocity in the y direction. So those two velocities end up giving you this resultant velocity at an angle, also known as the impact velocity, because that's the velocity it has, this angular velocity, when it impacts the ground. All right, so you know what to do next. Let's do it. If you don't know, you better know. You need an x, y table. We write down what we know. All right, we know the velocity in the x direction is what we're trying to solve. That's not zero. The velocity is what we're trying to solve. At the 20 meters, what's that describe? Oh, that's the height in the y direction equals 20 meters. All right, we land 36 meters away, so that's our delta x equals 36 meters. All right, do we know anything else? In the x direction, not really. 36 meters is velocity. In the y direction, we know how far it falls. This is 20 meters, from there to there. And we know, oh wait, it's accelerating because gravity. So we're going to say 10 meters per second squared. Technically it's negative because it's moving downward, so you can call this negative 10. And then because it's ball would be falling down as it goes, you could say it's going a distance of negative 20 meters. That's fine if you want to do that, but because they're both positive, or both negative, we can just call them both positive. You can cancel out those signs if you want. If you're not sure about that, come see me. All right. So do we know anything else? Yeah, we know the the initial velocity is 0 in the y direction because it's pure horizontal motion, no falling at first, just pure horizontal. So we would say the initial velocity in the vertical direction is 0. So can we find the final velocity? Well, because that's what we need here. The final velocity in the y direction. How fast will it be going down as it hits the ground? So we know that as objects fall, they go faster and faster and faster. this thing started at the top of its path, its downward velocity, I'm going to make this green so we can talk about this. The initial downward velocity in the y direction is 0. But we know 1 second later, it's traveling at 10 meters per second. And then 2 seconds later, it's traveling 20 meters per second, etc., etc. So things speed up. Things are faster when they hit the ground. So how do we find that? Well, we have a formula that says that, let me start that over, that says, and you guys got to have your formulas available. We know that the change in velocity equals acceleration times time. We know that from one of our big favorite triangles. Acceleration is delta v over t. Delta v is a times t. All right. But we don't have the time. We don't have the change in velocity. But I also know that delta v equals the final velocity minus the initial velocity. So because those things both are equal to each other, you can say that the final velocity minus the initial velocity is acceleration times time. And because the initial velocity is 0, we know that from the fact that it starts with pure horizontal motion. It means that we can now get rid of that. Really, it's just the final velocity is acceleration times time. Do we know the time? I think we do. Okay, but we do have, I'm going to go with a different color here. We do have the distance it's falling and the acceleration, and we know we're able to use our free fall equation, so we can say that the time equals the square root of 2 times delta y, the distance is falling, divided by the acceleration. So in this case, it's the square root of 2 times 20 meters divided by the acceleration, which is 10 meters per second squared. So t equals the square root of 2 times 20 is 40. Oh, look at the meters cancel out. Divided by 10. So it really equals the square root of 4, which really equals 2 seconds. So we can substitute that back up here. Come on now. So now we know that we know that the final velocity in the y direction is the acceleration times the time. Then we can say the final velocity in the y direction equals 10 meters per second squared times the 2 seconds that we found that it will be falling. So the final velocity in the y direction equals 20 meters per second. So that should be green, but I think you're with me. So the final velocity in the y direction is 20 meters per second. All right. Now what about the stuff in the x direction? Well, we have a time now. Time equals 2 seconds because however long it takes to fall at 20 meters is the same as the time it's moving back and forth in the x direction. So now we know that velocity equals change of position over time. Velocity equals 36 meters because that's how far it went in the x direction, divided by the 2 seconds it took to do that. So the velocity equals 18 meters per second. Sorry, that's really crowded. Hopefully it's okay. So we have 18 meters per second down there. So now we've got some important stuff. I'll try and highlight here. That, and that are going to team up for these. This is kind of where we're at right now. Now that we know, back to you, these very important bits here. we can find the rest. We just need to find the angle. So, do we have anything about the angle in the words? We do not, but we can find it because now we've got a triangle. I'm going to take the stuff that's in yellow and I'm going to move it so we can just see it a little bit more clearly. Let's get this out of here and blow it up over there. All right, so we know that we have a Vx of 18 meters per second. That's the horizontal velocity making this thing move to the right. Then we've got this Vy, which is making it go down to the ground, of 20 meters per second. Notice how I added those tip to tail. Got to do it that way. The horizontal velocity is to the right. The gravitational acceleration velocity is down, so you have to organize them this way. And from that, you get this resultant vector of whatever this angle is. So it's typical to do the angle from above the horizontal. That happens to be the same as below the horizontal on the other end. So either these are the same, prove that to yourself. The geometry's freaking you out, but you can handle it. So we're going to call this theta. And now we have to take a look at our SOHCAHTOA. Oh, by the way, at this point, you can either measure the stuff down with a ruler, if you have exactly 18 millimeters and 20 millimeters and an exact right angle, and you can measure the rest of the stuff with a protractor, and you'll be okay. But SOHCAHTOA is so much easier. So let me show you. We've got both of the short legs, so that's one of them has to be the opposite, one of them has to be the adjacent. By the way, here's the angle. The side that's on the opposite end of the triangle is opposite. The side that's next to it or adjacent to it is the adjacent. So we know that tangent of theta equals opposite over the adjacent. So tangent of theta equals, in this case, 20 over 18. That's okay to do, not put units in there because they cancel out. We have to get rid of the tangent, so we do that by taking the inverse tangent of that side. But if I do it here, I got to do it on the right side too. So I'm going to take the inverse tangent of that. And what these things do is the tangent inverse and the tangent cancel out, end up with the angle theta equals the inverse tangent of 20 over 18. So I'm going to pause this and calculate. I plug in, I hit my second button and then the tangent button, so it's tangent -1. Plug in 20 over 18 and I find out that it is 48.0 degrees, and I would say above or below horizontal. All right, so this tells us the angle, 48 degrees. Now what about the length of this? Well, this is where you can just bust out your Pythagorean theorem. Our resultant length is going to be equal to the square root of 20 squared plus 18 squared. And I'll let you do the algebra on your own, work out, actually it's just basic math. But real quick, I'm going to calculate it, and let me think, what could it be? Yes, 26.9 meters per second. Let's just call it 27 meters per second. There you go. That was a lot of stuff. You did great hanging in there. Remember, you can always pause these, rewind them, focus on one thing after another. Whatever works for you. I hope it's helpful. I'll try to do another one right away. All right, later.